locally at each server. Is this serial equivalent for transaction T? The answer is yes or no. Just look at transaction T. Is it serial equivalent? Yes, it's serial equivalent because you only have two operations, right? You write A and read B. This schedule, one is at server X and one is at server Y. Okay, and transaction U by itself is also serial equivalent, right? Because it has two commands. We can also look at this two transactions as what happened in the same server. So if we just look at server X and server X over here, we have transaction T and transaction U, right? Transaction T write A here, transaction U read A here. So transaction T and U, are they serial equivalent for the server X? Look at just server X. These two transactions T and U, are they serial equivalent? Are they serial equivalent? They are serial equivalent. Equivalent to what? Equivalent to what? Which happened first? T before U or U before T? T before U. Okay? And server X is T before U. Now, just look at server Y. Is a transaction T and U serial equivalent? Just look at server Y. Is it serial equivalent? Equivalent to what? U before T. Okay? So as server X is serial equivalent to T before U. As server Y is equivalent to U before T. At each individual server, they are serial equivalent locally. Okay? But if you look at both server X and Y, you found out that at one server is T before U and another server is U before T. Would that cause problem? Would that cause problem? Would this transaction cause problem? Now you look at this and tell me whether this transaction will cause problem. And what problem does it cause? What's the problem it caused? T write A at X. So what does it do? You will issue a write lock at server X to lock the data A, right? Now, the next time, transaction U will write B at Y. So what does it do? It will lock B at server Y. Okay? And because we are executing two-phase locking protocol, you don't release the lock. You have to acquire lock first. So T then will try to read B at Y. What happened? It was locked, right? So it has to wait here. Server U here will read A at X. What will happen? The is was locked. So you will wait. So both transactions will wait here, waiting for the other transaction to release the lock. This is called deadlock. Okay? So immediately you have deadlock. That is transaction T before transaction U at server X, transaction U before transaction T at server Y. Locally, they are serial equivalent, but globally, they have different order. We said that they are not serial equivalent globally, and when they are not serial equivalent globally, the result is that you will see there's a deadlock. Okay, so this is not serial equivalent globally since T before U in one server and U before T in another server. The problem is that it causes a deadlock. Let me give you another example here. For this, interleaving of transaction U, V, and W, for U, this D dot deposit means that you will deposit $10 to this variable D. That is, you add $10. B dot withdraw 30 means that you will deduct $30 for variable B. Okay. So for this example, again, schedule going from top down. Transaction U include these three operations. V include these two operations, and W include these two operations. So when you do the transaction, it will issue a lock for variable D, right? And V will issue a lock for variable B. Okay, and U here, when going down, you will issue another lock for variable A, and W here going down here will issue a lock for variable C, and then you want to withdraw $30 from B. So you will issue a lock, but it's already locked by process V. So you have to wait for process V to complete. And on the other hand, V execute over here, then you want to lock variable C, but variable C was locked by the transaction W. So transaction V wait for transaction W to complete, and transaction W continues that it wants to withdraw $20. Then this variable A was locked by transaction U. So W wait for transaction U to complete. You have the cycle of these three transactions. U wait for V, V waits for W, and W waits for U. Also deadlock. So you can see that the deadlock involves a cycle that transactions are mutually waiting for each other to complete. And this cycle can be a big cycle. So detecting a deadlock is not an easy problem because there could be a lot of transactions, right? So we are going to talk about how we resolve the deadlock situation. These are sort of the things that I just explained earlier. So for this kind of deadlock, we call it distributed deadlock because deadlock occur among multiple transactions. How do we detect the distributed deadlock? We need to draw the waveflow graph. In other words, the situation where we have W waits for U, U waits for V, V waits for W. This is a waveflow graph. To detect that, we need to analyze the transaction situation where in the previous diagram, we noticed that the transaction, the C was held by W, and W wait for A to be released. But A was held by U, okay? And D was also held by U, and it is waiting for Y to be released, but Y was held by V, okay? And then V waits for C to be released. In turn, it waits for W. So this kind of situation, simplified as this waveflow graph, we have to be able to detect that. How do we detect the waveflow graph? We need to have local and global waveflow graphs. So for the local waveflow graphs, that is in each server, you can detect that one waits for the other one. Server X, we have transaction T waits for transaction U, like the previous diagram. For the server B, we know that transaction V waits for transaction W. At the server X, we know transaction W waits for transaction U. And at server Y, we know that U waits for V. That's why we have this kind of waveflow curve, waveflow graph, and we detect the cycle there. So locally, we can say at server X, T waits for U, and at server Y, V waits for T. So these are local observation. But we need to have a global picture, right? So a global picture means that we need to have a global deadlock detector. If there's a global deadlock detector, we may see that because at server X, T waits for U, and at server Y, V waits for T. So we have this V waits for T, T waits for U. That here arrow is just meaning wait for. Okay? Arrow is often used in this course. Sometimes it is happened before kind of thing. In here it's just wait for kind of thing. So wait for and happen before, these are two different kind of concepts. Okay, don't mix them. So here, V waits for T, T waits for U, and we said that in this situation we may have phantom deadlock. Phantom deadlock means a deadlock that is detected, but it's not really a deadlock. We call that as a phantom deadlock. Why would that be a phantom deadlock? Because your global deadlock detector may not detect the situation quick enough. This example shows the following. For example, if transaction U release this object at server X, that is T no longer wait for U. Okay, but at the same time you will request an object held by V at server Y. Okay, so if U requests something held by server Y, so U will wait for V to complete. Okay, if it is a release, but you also request something at server Y, and server Y something held by V at server Y, then U will wait for V. If the second situation that you wait for V arrive at the global deadlock detector earlier than the release of this lock, then you merely add an arrow, you wait for V here, but in fact, the fact that T wait for U was already released, right? This T wait for U, T wait for V, this is already released. So U wait for V will not have the deadlock. But if you actually global detector have added this arrow first before it even delete it, then global deadlock detector may say that, hey, there's a deadlock. But in fact, there's no deadlock. This kind of thing is called phantom deadlock. Is that clear? Okay. Because global deadlock detector, there's no guarantee that the transaction T releases object first and then requests another object held by V. It cannot guarantee that this one will be detected before the other one. So you may, in fact, add this arrow before you remove that arrow. If that's the case, then global deadlock detector may have mistakenly think that there's a deadlock, but in fact, actually there's no deadlock. And this situation is called phantom deadlock phantom deadlock. So in other words, if the global deadlock detector was not properly designed, then you will have phantom deadlock. Okay, and that's usually not easy way to have a global deadlock detector to be detected properly, because the global detector eventually is you need to find the deadlock by a distributed way to collect global information. But global information, these are distributed, and it takes time for information to travel from one place to another place, so that you cannot guarantee this kind of information may arrive in the proper order. That's why phantom deadlock may have occurred. So whenever there's no deadlock, but you thought there's a deadlock, what will happen? When there's a deadlock, what do you need to do? You have to undo some processes, right? So you will actually, and sometimes you need to roll back. There's a lot of overhead. And when there's no deadlock, you thought there's a deadlock, you are wasting the resource for the overhead. Okay? Is that okay so far? All right. And phantom deadlock here also give you another reason why the two-phase locking is a good protocol. Okay. Why is two-phase locking a good protocol? Comparing with this phantom deadlock here, in other words, can phantom deadlock occur in two-phase locking? We talked about two-phase locking 2 weeks ago, and I just introduced a phantom deadlock to you. So my question is, can phantom deadlock occur in two-phase locking protocol? Can it occur? The answer is the answer is phantom deadlock cannot occur in two-phase locking. Take this as an example. Can you tell me why? Phantom deadlock occur because in this example, because transaction you what? You release lock and then acquire another lock. Is that allowed in two-phase locking? No. Remember, two-phase locking is that when you acquire lock, you don't release them, right? When you release a lock, you cannot acquire any more lock. That's why there's a growing phase and there's a completion phase, right? That is, two-phase locking is that the number of lock gradually increase and then sharply decrease can only increase the lock, and once you start release it, you cannot acquire. That's why the curve only go up, and it shall be dropped, right? And this is not allowed in two-phase locking. Okay? So there's no phantom deadlock in two-phase locking. Okay? In other words, the deadlock, can deadlock occur in two-phase locking, by the way? Can deadlock occur in two-phase locking? Yes, okay? Yes, so any deadlock occur in two-phase locking is real deadlock. You really have the deadlock and you have to redo the process. You don't have phantom deadlock in two-phase locking. Alright, so this is the additional thing that we want to talk about. Alright, so how do we detect the deadlock? How is a global deadlock detector to be formed? This is one example. You usually send out probe travel from one server to the other server and collect the waveform information. So we can have the following situation. That is, we may start with the deadlock detector as a probe. Probe is a small process that will send out to collect information. So we may initiate the deadlock detector here. So at server X, we know who is waiting for whom. At server X, which transaction waits for which transaction? W waits for U, right? So you will send a message to server B, carry W waits for U here. Okay. So at server B, you have additional information. Who waits for who? V waits for U, right? So now you have W waits for U, and U waits for V. I should say U waits for V, not V waits for U. U waits for V. So that additional information can follow to send the server C over here. Okay? At server C, which transaction waits for which transaction? V waits for W. So here then you have the situation, W waits for U, U waits for V, V waits for W. There's a cycle, so deadlock is detected here. A probe is issued from this server X, travel to Y and Z, then you collect the information about a cycle in the waveform graph and detect the deadlock. So typically it's done this way. You need to send a probe, travel around to collect local information from each server so you have a global picture. Okay, so we call this as the edge chasing algorithm. You have edge chasing algorithm because here you know W waits for at server X, you know W waits for U, because and then because you know that you want to find out what transaction U has been waiting for, right? So in that way, you need to send a probe along the edges in order to have a construction of the waveform graph, so that you can go to this edge and go to the edge, so that at another server you have the information. So this edge tracing algorithm, you have initiation server, and then you have detection at another server, and finally you need to do resolution. Often resolution in the deadlock. How to resolve a deadlock? We also mentioned about that. How do we break for the waveform thing? You need to abort one of the transactions. When you abort one of the transactions, then you don't have the cycle in the waveform graph. The other transaction may complete, okay, so that you can have the smooth execution. Otherwise, everybody is waiting for other transactions to complete. This kind of global deadlock detector sending probes may have the following problems. The problem is the following. You may, the reason why you send a probe to detect whether there's a deadlock or not is because that you found out that transaction cannot move, right? So you send out probe to find out if there's a waveform graph has a cycle. So in that case, because different server, in fact, participate in a transaction, may be waiting already long. So two servers may at the same time send out the probe. And when two probes are being sent out, for example, V waits for T and U waits for W, at two servers, two probe may be sent out at the same time. So then you can have detection initiated by object requested by server by transaction T. So in that way, you have sent out the probe, T waits for U and U waits for W, W waits for V, so that you have detection. You send out the probe, wait for graph here, and then detect it right here. Okay, and this time you find out that V in turn wait for W. So you send out here and then wait, detect that in this server for the sort of the cycle in the waveform. And you may also send out another probe, detection initiated an object requested by W. You may send a waveform graph here. You know that W waits for V, and then here you collect that V waits for T, and right here you collect that T waits for U. And at this moment you know that U also waits for W. You can detect that. So you can send out this probe at the same time by two different servers and detect the deadlock at the same time. Okay, this could be the potential problem. And if this occurs, then you may have mistakenly to abort two transactions instead of aborting one. Right? Both of them say, oh, there's a deadlock, we need to abort transactions. So they may abort two transactions, but instead you only need to abort one transaction. Okay, so this is sort of the possible disadvantage for this sending out the probe. But this kind of disadvantage can be easily removed. Okay, so tell me, how can you avoid the situation that two probes will delete two different transactions? You don't want to delete two different transactions, abort two different transactions. You only need to abort one transaction, right? So how can you have the situation that they only abort one transaction? That is, they need to know they only abort the same transaction. Then they only abort one transaction, right? So how do they know to abort the same transaction? How do you do that? Remember, the transaction has what? Every transaction has what? A unique what? Identifier, right? So you can just run a protocol that all the transaction when you want to abort, you abort the transaction with the, say, largest identifier. Usually an identifier also carry the timestamp kind of idea. Larger number means a later transaction, right? They can agree to abort the most recent transaction, so the one with the largest number. And in that case, they will not abort two different transactions. So this one will be fine. Okay. All right. So pretty much I complete the discussion and in time. That is, we talk about tonight regarding transaction concept. So there's an ACID property, and we talk about transactional comments. What are the three transactional comments? Begin, and then transaction comments. Begin, abort, commit, right? And abort and commit, they are also called end of transaction, right? Okay, and roles of distributed component in transaction. What are the three roles? Coordinator, participant include, participant is also known as transactional server, and they are client of the transaction called transactional client. The transactional client, everything has to be transparent to the transactional client, so important thing is about the server and participant, or the transactional server, and the coordinator and transactional server, okay? And they need to form a two-phase commit protocol. And this two-phase commit protocol has two phase, loading phase and completion phase. And distributed transaction, distributed deadlock is that distributed transaction have their interleaving, and interleaving need to have the sort of serializability, serial schedule, not locally, but also globally, in order to avoid the deadlock. And how do we detect there's a deadlock? We can do the distributed deadlock using the detection as, say, sending out the probe, okay? And but there are issues related to that we just discussed. All right. So all this come from the textbook chapter 16 and 17 as a result. All right, any question about today's lecture? Any question? All right, we have about 5 minutes left, and so let me, maybe I can go to the first lecture, and then we can look at our schedule, sort of in a way that showing to you about what we cover. So we cover the topic 1 through topic 7 as we have discussed. Okay. So if I quickly give you the midterm thing, remember midterm will be next week right here. I will give you 3 hours. So please arrive in time, 7 o'clock, and we can do that all the way until 10 o'clock. Okay, you have 3 hours, and roughly we will have about say 1 question per topic, roughly speaking. Okay, and so we may have a problem here, and a problem here, one problem here, one problem here, one here, and one here. Okay, so about 5 or 6 problems, even one for each topic. But there are issues that is I consider more important. In characterization of distributed system, you need to know those properties related to distributed systems and the features associated with that. For the second one, I'm more interested in knowing how you understand the communication. Okay, what are the communication type? You have R protocol, RA protocol. Why are there these different protocols? Right? What's the purpose of those? Okay, and what's the usage of, say, acknowledgement, which is important in distributed systems, and communication pattern as well, right? Remember, those are the features. Okay, the third topic is one of my favorite topics, okay, because it's easy to give questions that is interesting enough. So in the security, you need to understand important cryptography technique, like RSA algorithm in class practice and also in the exercise. You have done that. You need to know that, but you also need to know other kind of security protocols. Okay, and here I will give a question related to a certain protocol and want you to execute a detailed communication pattern, which is using some security things here, security protocol. So there was key distribution kind of thing, those kind of ideas. You need to know it well. So there will be a very solid problem on security. Okay. Solid problem means that you need to spend time and understand it quite well to get it done enough. Well-defined problem. Okay. And then naming, trading, and P2P system. You need to know the difference in between naming and the trading. There's no programming kind of problems for you. So it's all either algorithms or the conceptual kind of problems. So don't worry about the programming thing. And how does P2P system work in general, and why does it work? Okay, topic number 5 is also an important topic. Okay. The concept about the time, the notation of time, particularly the Lamport clock and vector clock, and how does each work, and what are the properties of Lamport clock and vector clock. These are kind of important. And of course, we also, in that part, we have how to achieve agreement, how to do coordination. These are also kind of important thing. And another important issue, I think we addressed that in the also in that part. will be, if you remember, we have ordering, right? Total order, causal order, and this total order, causal order. There are three order, five order. Thank you. Okay, so this ordering are quite important. Understanding the ordering, I may give you a real examples to see, use different kind of ordering, what would be the value that was passed from one processor to the other processor, okay? And whether the ordering can be guaranteed. So there could be real value computation, and you see the effect of the ordering. Okay. I gave you definition in those ordering thing, but the example I may give you so that you show the clear about the true effect. Okay, so knowing, understanding the definition of the ordering is important. I think that was topic number 5. In other words, topic number 5, because there is multiple things there. There could be two problems. So I'm saying that some topic may not have a problem. I just say which one is more important there. Okay, some important topic may have two problems. Okay, the concurrency control is essentially the two-phase locking protocol. You need to know how two-phase locking protocol works, okay? And why are there two-phase locking? Okay? And also, in this two-phase locking, we also talk about the different lock mode. What's the meaning of each lock mode? These are the things 2 weeks ago, I think I went through them in detail. Okay? And today we talk about a transaction which is essentially a two-phase commit protocol. In your exercise, you can see a problem. By the way, exercise is good practice for you, even though it's due after the midterm. Right? So it will be a good practice for you to see there may be related or similar problems in your midterm. And the two-phase locking in your homework, there is something different locking procedure. I'm sorry, two-phase commit. There are other kind of protocol. So you need to understand the two-phase commit protocol, the complexity of that, how does it work, and pros and cons, and also the flag transaction, the nested transaction, the special case in the nested transaction. Okay, we already exercised the nested transaction. How does it work? Eventually, how would the subtransaction know whether it can commit or abort? You know, the idea that at the end, there is also a flat two-phase commit protocol to determine the outcome of a nested transaction. Okay. And that was what we just covered. Okay. So these are sort of the important we talked about. Is that a good enough hint to you? Or is it still too vague? Okay, so here's a time for you to ask questions.
Can we take the notes?
I already told you that it's a 1 A4 size. You cannot take all the notes. If you take all the notes, everybody may get a full mark. So I want you to sort of follow by, we have that specification. No, not here?
Oh, not mentioned before.
Alright, so you see, open 1 A4 size paper, topic 1 to 7, not 8. Sorry, so there was a typo. Today's topic is 7, okay? So this is topic 1 to 7. But open 1 A4 size paper means that you only print 1 page. But I know undergrad students are so smart, they put everything in that 1 page. No, that's
one side. Right.
Only one page. Both double side is fine.
Double side.
But in fact, this exam, time is more important. Even 3 hours given to you. Some student, time is enough. But I just want to make sure that all of you have enough time, okay, to address all the problems. But to some of you, you may think 3 hours is still not enough. Okay. So in other words, if you take it as a closed book exam, because closed book exam, you don't waste time finding always answer in the solution, right? You're just working out. Then it may turn out that you can score better than open book. In other words, if you follow my lecture, then for each question, you can directly answer that. I don't think in general you need to memorize things. But of course, there could be something hard to remember, but you consider it important and put it into the notes. In other words, there's really no need to do like undergrad student, where they have one note to include all the notes in the class. They put very small thing and jam there. That's not very helpful, I will tell you, for this class. In other words, as I said, you take this as a closed book, closed note exam. If you study the material well enough, you still can score very well. I think it's about 5 or 6. But each question has sub-questions. So when you come in, okay, it's important that you cannot have any seat in your neighbor to be occupied. So I like that people to have, say, one row here, right, and then one row here, okay, and then 2 seats here, 1 row here, okay, and 1 row here. So 1 row here, 2 row here separated, and 1 row there. So just 1 row, straight row. Okay?
Very strict isolation.
And we will do that in this classroom. Just work out everything by yourself. Don't bring telephone or anything that can communicate. Okay? You are allowed to use a small, simple calculator, but not a mobile phone. In any case, calculator may not be useful, but if you feel comfortable to bring it, I didn't say you are allowed it, right? If you feel that you like to have a calculator, even say 2 times 5, you need to use a calculator to figure that out and put in the calculator. Yeah. But otherwise, you don't really need a calculator. Okay, only simple calculator, but not a phone. Otherwise, no need to bring calculator. Any questions? I won't be here for the exam. The tutor will come over to investigate the exam. And the tutor can answer the question about the exam problems anyway. So, okay? Is that okay? Yes?
Is homework more difficult or the questions?
Homework is generally more difficult than the midterm homework, generally. But the midterm is not exactly the same pattern you have seen. Okay, I can say that maybe half or a bit more than half are the same pattern you have seen, either in the homework exercise or in the in-class practice. But there will be about half of them you haven't seen the pattern yet. Okay? But you should be able to understand it if you understand the course contents that I have conducted so far. Okay? And every part of the lecture may be important. That is, there could be, the hint is there could be one of the slides, I already explained that slide, the algorithm, everything, and then for that slide, I will give real numbers on that slide so that you work out a real example based on the algorithm of that slide, for example. Okay, it could happen that way. So when I explain the slide, it could be just all symbols, and the homework may be just making all the symbols as real number thing you carry out some computation. A slide may be an algorithm, and this algorithm exam may be the algorithm is a real example given to you to carry out things. It could be something like that.
Real example.
For example, I can give you a nested transactions. I gave you something in today's class, right? I can give you another massive transaction and tell you which one provisional for, and at the end you tell me what are these things, for example. Right? So everything come out from one slide as just detail as a different example. I could do that. In other words, if you understand contents well, then you can work out the problem, but it will take time because the case might be complicated. But the mechanism, if you understand complicated example, you still can work out the detail. Just take time. It's not something that you look at that and you say, you have no idea how it works. I will not give an example about a cryptography algorithm which I didn't teach you yet. And it's very hard to figure out. Okay. Other questions or anything? Is that okay? I will. Yeah, I'll post the solution. I'll post the solution for. If I miss anything, just email me. Okay. In other words, for topic 1 to 7 and in-class exercise, you should have all the detail, except the homework assignment 2, because it's due later on, so the solution is not given to you. Okay? All right, if you don't have question, then good luck on your midterm exam. I will see you 2 weeks later. Okay? All right, good luck. And take care. Make sure you submit your proposal by midnight tonight, okay?